So before we embark on the analysis, what are we hoping to understand? Well, what seems intuitively clear is that there's going to be some trade-off between the two resources of a Bloom filter. One resource is space consumption, the other resource is essentially correctness. So the more space we use, the larger number of bits, we'd hope that we'd make fewer and fewer errors. And then as we compress the table more and more, reuse bits more and more for different objects, then presumably the error rate is going to increase. So the goal of the analysis that we're about to do is to understand this trade-off precisely at a quantitative level. Once we understand the trade-off curve between these two resources, then we can ask, is there a sweet spot which gives us a useful data structure? Quite small space and quite manageable error probability. So the way we're going to proceed with the analysis will be familiar to those of you that watched the open addressing video about hash tables. So to make the mathematical analysis tractable, I'm going to make a heuristic assumption. It's a strong assumption which is really not satisfied by hash functions you would use in practice. We're going to use that assumption to derive a performance guarantee for Bloom filters. But as always in any implementation, you should check that your implementation actually is getting performance comparable to what the idealized analysis should suggest. That said, if you use a good hash function and if you have non-pathological data, the hopes, and this is borne out in many empirical studies, is that you will see performance comparable to what this heuristic analysis will suggest. So what is the heuristic assumption? Well, it's going to be, again, familiar from our hashing discussion. We're just going to assume that all the hashing is totally random. So for each choice of a hash function hi and for each possible object x, the slot, the position of the array, which the hash function gives for that object, is uniform at random, first of all, and it's independent from all other outputs of all hash functions on all objects. So the setup then is we have n bits, we have a data set, capital S, which we've inserted into our Bloom filter. Now our eventual goal is to understand the error rate, or the false positive probability. That is, the chance that an object which we haven't inserted into the Bloom filter looks as if it has been inserted into the Bloom filter. But as a preliminary step, I want to ask about the population of ones after we've inserted this dataset capital S into the Bloom filter. So specifically, let's focus on a particular position of the array, and by symmetry it doesn't matter which one, and let's ask what is the probability that a given bit, a given position in this array, has been set to 1 after we've inserted this entire dataset capital S. All right, so this is a somewhat difficult quiz question, actually. The correct answer is the second answer. It's 1 minus quantity, 1 minus 1 over n raised to the number of hash functions k times the number of objects, the cardinality of s. That's the probability that, say, the first bit of a Bloom filter has been set to 1 after the dataset capital S has been inserted. So the maybe easiest way to see this is to first focus on the first answer. So the first answer is going to be the probability, I claim, that the first bit is 0 after the entire data set has been inserted. Then, of course, the probability that's 1 is just 1 minus this quantity, which is equal to the second answer. So we just need to understand why the first choice is the probability that the first bit equals 0. Well, it's initially 0, and remember, stuff is only set from 0 to 1. So we need to analyze the probability that this first bit survives all of these darts that are getting thrown to the Bloom filter over the course of this entire data set being inserted. So there are these cardinality of S objects, each get inserted. On an insertion, k darts, uniformly at random and independent from each other, are effectively thrown at the array, at the Bloom filter. Any position that a dart hits gets set to 1. Maybe it was 1 already, but if it was 0, it gets set to 1. If it's 1, it stays 1. So how is this first bit going to stay 0? Well, it has to be missed by all of the darts. A given dart, a given bit flip, is uniformly likely to be any of the n bits. So the probability that winds up being this bit is only 1 over n. The probability that it's fortunately somebody else, well, that's 1 minus 1 over n. So you have a chance of surviving a single dart with probability 1 minus 1 over n. There's the number of hash functions k times the number of objects, cardinality of S darts being thrown, right? K per object that gets inserted. So the overall probability of eluding all of the darts is 1 minus 1 over n raised to the number of hash functions k times the number of insertions, cardinality of S. And again, the probability that it's 1 is just 1 minus that quantity, which is the second option in the quiz. So let's go ahead and resume our analysis using the answer to that quiz. So what did we discover? We discovered the probability that a given bit is 1 minus quantity 1 minus 1 over n, where n is the number of positions raised to the number of hash functions k times the number of insertions, cardinality of S. So that's a kind of messy quantity. So let's recall a simple estimation fact that we used once earlier. You saw this when we analyzed Kargar's contraction algorithm and the benefit of multiple repetitions of Kargar's contraction algorithm. And the trick here is to estimate a quantity that's of the form 1 plus x or 1 minus x by e to the x, or e to the minus x, as the case may be. So if you take the function 1 plus x, which goes through the points minus 1, 0 and 0, 1, and of course is a straight line, and then you also look at the function e to the x, well, those two functions are going to kiss at the point 0, comma 1, and everywhere else e to the x is going to be above 1 plus x. So for any real value of x, we can always upper bound the quantity 1 plus x by e to the minus x. So let's apply this fact to this quantity here, 1 minus 1 over n raised to the k times cardinality of s. We're going to take x to be minus 1 over n. So that gives us an upper bound on this probability of 1 minus e to the minus k times the number of insertions over n. Okay, so that's taking x to be minus 1 over n. Let's simplify our lives a little bit further by introducing some notation. So I'm going to let b denote the number of bits that we're using per object. So this is the quantity I was telling you to think about as 8 previously. This is the ratio n, the total number of bits, divided by the cardinality of s. So this green expression becomes 1 minus e to the minus k over b, where b is the number of bits per object. And now we're already seeing the type of trade-off that we were expecting. Remember, we were expecting that as we use more and more space, then the error rate we think should go down. So if you compress the table a lot, so you reuse bits for lots of different objects, that's when you start going to see a lot of false positives. So in this light blue expression, if you take the number of bits per object, so the number of space, the amount of space, little b, if you take that growing very large, tending to infinity, this exponent tends to 0, so e to the minus 0 is 1, so overall this probability of a given bit being 1 is tending to 0. So that is, the more bits you have, the bigger space you have, the smaller the fraction of ones, the bigger the fraction of zeros. That should translate to a smaller false positive probability, and that's what we'll make precise on the next and final slide. So let's rewrite the upshot from the last slide. The probability that a given bit is equal to 1 is bounded above by 1 minus e to the minus k over b, where k is the number of hash functions and b is the number of bits we're using per object. Now this is not the quantity we care about. The quantity we care about is a false positive probability, where something looks like it's in the Bloom filter even though it's never been inserted. So let's focus on some object like some IP address which has never ever been inserted into this Bloom filter. So for a given object x, which is not in the data set, that is, has not been inserted into the Bloom filter, what has to happen for us to have a successful lookup, a false positive, for this object? Well, each one of its k bits has to be set to 1. So we already computed the probability that a given bit is set to 1. So what has to happen for all k of the bits that indicate x's membership in the Bloom filter, all k of them have to be set to 1. So we just take the quantity we computed on the previous slide and we raise that to the kth power, indicating that it has to happen k different times. So believe it or not, we now have exactly what we wanted, what we set out to do, which is derive a quantitative understanding of the intuitive trade-off between, on the one hand, the space used, and on the other hand, on the error probability, the false positive probability. So we're going to call this green circled quantity a name. We'll call it epsilon for the error rate, and again, all errors are false positives. And again, as b goes to infinity, as we use more and more space, this exponent goes to 0, so 1 minus e to that quantity is going to 0 as well, and of course once we power it to the kth power, it gets even closer to 0. So the bigger b gets, the smaller this error rate epsilon gets. So now let's get to the punchline. So remember, the question is this data structure actually useful? Can we actually set all of the parameters in a way that we get both really usefully small space, but a tolerable error epsilon? And, of course, we wouldn't be giving this video if the answer wasn't yes. Now, one thing I've been alluding all along is, how do we set k? How do we choose the number of hash functions? I told you at the very beginning to think of k as a small constant, like 2, 3, 4, 5. And now that we have this really nice quantitative version of how the error rate and the space trade off with each other, we can answer how to set k. Namely, set k optimally. So what do I mean? Well, fix the number of bits that you're using per object, 8, 16, 24, whatever. For fixed b, you can just choose the k that minimizes this green quantity, that minimizes the error rate epsilon. So how do you minimize this quantity? Well, you do it just like you learn in calculus, and I'll leave this as an exercise for you to do in the privacy of your own home. But for fixed b, the way to get this green quantity epsilon as small as possible is to set the number of hash functions k to be roughly the natural log of 2, that's a number less than 1, notice, that's like 0.693, times b. So in other words, the number of hash functions for the optimal implementation of a Bloom filter is scaling linearly with the number of bits that you're using per object. It's about 0.693 times the bits per object. Of course, this is generally not going to be an integer, so you just pick k to be either this number rounded up or this number rounded down. But continuing the heuristic analysis, now that we know how to set k optimally to minimize the error for a given amount of space, we can plug that value of k back in and see, well, how does the space and the error rate trade off against each other? And we get a very nice answer. Specifically, we get that the error rate epsilon, this is under an optimal choice of the number of hash functions k, decreases exponentially in the number of bits that you use per object. So it's roughly 1/2 raised to the natural log of 2, or 0.693 roughly, times the number of bits per object b. But again, the key qualitative point here is to notice that epsilon is going down really quickly as you scale b. If you double the number of bits that you're allocating per object, you're squaring the error rate. And for small error rates, squaring it makes it much, much, much smaller. And of course, this is just one equation in 2 variables. If you prefer, you can solve this equation to express b, the space requirement, as a function of an error requirement. So if you know that the tolerance for false positives in your application is 1%, you can just solve this for b and figure out how many bits per object you need to allocate. And so rewriting, what you get is that the number of bits per object that you need is roughly 1.44 times the log base 2 of 1 over epsilon. So as expected, as epsilon gets smaller and smaller, you want fewer and fewer errors, the space requirements will increase. So the final question is it a useful data structure? Can you set all the parameters so that you get a really interesting space error trade-off? And the answer is totally. So let me give you an example. Let's go back to having 8 bits of storage per object, so that corresponds to b equals 8. Then what this pink formula indicates is we should use 5 or 6 hash functions. And already you have an error probability of something like 2%, which for a lot of the motivating applications we talked about is already good enough. And again, if you double the number of bits to say 16 per object, then this error probability would be really small. It would be pushing 1 in 5,000 or something like that. So to conclude, at least in this idealized analysis, which again you should check against in any real-world implementation, although empirically it is definitely achievable with well-implemented Bloom filters and non-pathological data, to get this kind of performance, even with really a ridiculously minuscule amount of space per object, much less generally than storing the object itself, you can get fast inserts, fast lookups. You do have to have false positives, but with a very controllable amount of error rates, and that's what makes Bloom filters a win in a number of applications.